All right, in this presentation, we'll talk more about ligands, and I'll share my slides with you now. Here we go. So ligands, remember, are those molecules or ions that can have their own existence, but in this case are attached to a central metal atom or ion. And they are coordinated through that lone pair of electrons on the ligand. So keep that in mind as we're looking at each of these compounds, and go back and refresh your memory if you've forgotten what a Lewis acid and a Lewis base are. So all right, so let's talk about ligands and denticity. So ligands, remember, we just talked about, are the things attached to the metals, and denticity has to do with how they are attached to the metals. So monodentate ligands, and dentate means something like teeth or bite. Monodentate ligands have a single donor pair of electrons and have only a single point of attachment to the metal. So ammonia, like we looked at before, water, bromide, and hydroxide are examples of monodentate ligands. Dentate ligands have more than one point of attachment to a metal. So this ligand on the left, which has this name, which is often called ACAC, has two oxygens, which have, of course, two lone pairs of electrons in each case. And these oxygens are able to both bond metal at the same time, and it's said to be a ligand. And ethylene diamine over here, each nitrogen has a lone pair of electrons, and so those lone pairs can interact with a metal ion. In addition to the numbers of lone pairs of electrons, we have to consider the size and the geometry of the molecule that we're talking about. In this case, both of these are set up to nicely bond to one metal atom in the center. So we can have tridentate ligands, called diethylene triamine, this one here, and it can bind through each of these sort of pendant nitrogens here and through this nitrogen as well. And cyclam, which is this molecule shown here, is tetradentate, and you probably already guessed that these nitrogens, which of course have lone pairs of electrons, are going to interact with the central metal. So you can have a central metal atom or ion here, and it can interact with all four of these nitrogens. So when a polydentate ligand binds to a metal, it forms what's called a chelate, which is a ring that includes the metal atom. So this is a five-membered ring. It has the metal here, and then this is ethylene diamine again in a ring. So the bite angle is the angle between this part of the ligand to the metal back to the ligand. Ambidentate ligands have more than one donor atom. So thiocyanate and isothiocyanate are ligands that you probably encountered in general chemistry. And it's called thiocyanate if it binds through the sulfur, which is at one end, and isothiocyanate if it binds through the nitrogen at the other end. Even though these two have lone pairs at both ends, the compound is so small that it can't bind at both ends at the same time. So it isn't polydentate. It's ambidentate, though, because it can bind at either end. Nitro is NO2 minus binding through the nitrogen, and nitrito is the same ligand but binding through the oxygen end. There is also a table in your book, but there are 10 ligands that you are responsible for knowing the names of. ACAC, so acetyl acetonato is the name of the ligand, or we call it ACAC. You need to know that one. It binds through oxygen, and it has two donors, or it is a bidentate ligand. We've talked about ammonia before. As a ligand, ammonia is called amine, and it is spelled with two M's to differentiate it from an organic functional group and amine group. So amine is a ligand. It binds through the nitrogen one donor group, it is a monodentate ligand. Water as a ligand is called aqua. In the older literature, and it's still quite commonly used, this is actually aquo. It's the same thing. It's just a difference in nomenclature due to the international rules. Water binds through the oxygen, and it's a monodentate ligand. 2,2-bipyridine is this compound here. It's called BIPI. It binds through each of the nitrogens and is bidentate. Carbon monoxide as a ligand is called a carbonyl. It binds through the carbon and has a single point where it binds. Cyano group, CN minus, right? So cyanide ion is called a cyano group. Binds through the carbon and is monodentate. Ethylene diamine, so that's abbreviated as EN, and it binds through each of the nitrogens so that it is bidentate. A hydroxyl ion is called a hydroxo group, binds through the oxygen one time, it's monodentate. An oxalate ion is called oxalato, and it's this group here. It's abbreviated OX, binds through the oxygens and two oxygens on one side, so it's bidentate. And the thiocyanato is the SCN ion. Thiocyanato, so when it's called that, it binds through the S. Isothiocyaнаto binds through the nitrogen, and that's monodentate in either case. So these are the ones that you are responsible for. You should know the names and the structures and whether they're mono or bidentate. All right, so we have some very complicated naming rules for coordination compounds. To be perfectly honest, coordination compound names are so complex that in most papers, the name is given once and then the formula is used for the rest of the paper. But we need to know how to name them because the names do come up. So we always name the cation before the anion. This seems like it might be sort of a funny rule, but it's actually a rule that you've been using and you might not be aware of. So if we have an ionic compound like sodium chloride or potassium chloride or potassium bromide, we've named all of those with the cation first and then the anion. We use the same rule here. So when we name the complex ion, we name the ligands first in alphabetical order, atom or the ion, the metal. So we use Greek prefixes to indicate the number of each type of ligand. The ligand name is what's alphabetized, not the prefixes. Then we name the central metal. And if the complex ion is a positively charged ion, the metal is named the same way as the element. Or if it's an anion, we change the ending to ATE. And finally, after the name of the metal, we indicate the oxidation state of the metal using a Roman numeral. So you did this in general chemistry. You might not have done it since general chemistry. And you probably didn't name coordination compounds. You probably named maybe some transition metal ions or something like iron chloride, for example, which technically would be iron 2 chloride or iron 3 chloride. So let's look at a couple of examples. I'll have to excuse my terrible writing again, but in this particular context, it just works better than typing the names up there. Right? So in this complex, we have NH3, and NH3 is amine. And we have H2O, which is water, but we call it aqua. as a ligand. Okay. Remember, the complex ion is what's inside the square brackets, so we're going to name that part first. We need to figure out whether this is positively or negatively charged. We have 3 chlorides as counter ions. And so the overall charge of what's inside the square brackets must, since this is 3 negative charges, this must be +3 for the whole complex ion. So this is positively charged, or a cation. So we have amine and we have aqua. So the amine comes first. So this is triamine. Triamine. We have 3 waters, so that's tri. Oops, TRI. Aqua. Then we name the metal chromium. And then we need to put the charge. Amine is ammonia. It has no charge. Water, or aqua, has no charge. The overall ion has a +3 charge, because we know that because the counter ions have a -3 charge. And so the chromium itself must be +3. So we use Roman numeral 3. Okay. So our complex ion is triamine, triaqua, chromium 3. And then we name our counter ion chloride. Phew. So our coordination compound is triamine, triaqua, chromium 3 chloride. All right, so let's name this one, but not try to write it down like that. Remember, this one has sodium as the counter ion, so that's positively charged, and the complex ion must then be negatively charged. Okay, so we would call this sodium, and then we name the complex ion, because remember, we always name the positively charged or cation first. So now we have 4 chloride or chloro ligands. So this is sodium tetrachloronickelate. And then we need the charge on the nickel. The chlorides each contribute -1, so that's -4. And the sodiums contribute 1 each, so that's +2. So the nickel must be +2. So this is sodium tetrachloronickelate. All right. So just a reminder of the prefixes, and then a special note about how we use them in inorganic compounds. So the the Greek prefixes are in the table down here if you've forgotten what they are. And in parentheses are the special ones that we use in a certain case. So some of the ligand names already contain a Greek prefix. So ethylene diamine is an example. And polydentate ligands, we also use these. Instead of, if we had 2 ethylene diamine ligands, instead of using di again, which might be confusing, we use bis. So it would be bis-ethylene diamine if we had 2 of them. And there's a particular example down here for this platinum complex, chloro bis-ethylene diamine, platinum 4 chloride. Okay. So if we had 3, it would be tris instead of instead of tri, or if we had 4, it would be tetrakis instead of tetra. So you should be aware of these special prefixes for cases where the ligand already includes that prefix, or if we have a polydentate ligand. All right, so we can have many different kinds of isomers, and we need to have names for these. So linkage isomers occur if we have ambidentate ligands. So we can have this nitrido ligand attaching through the nitrogen or through the oxygen, and we need to be able to communicate that to each other. So those would be linkage isomers. Ionization isomers happen when the ligand and the counter ion change places. So in the two examples here, or in the two complexes here, initially the chlorides are attached to the platinum. They're inside the bracket, so they're inner sphere. And the bromides are the counter ions. Ionization isomer has the bromides as the inner sphere ligands, so they're attached to the platinum, and the chlorides as the outer sphere or counter ions. So we can have hydrate isomers, and that occurs where we basically have the ligands and the counter ions changing places, but one of the ligands is water. And so there are some examples shown here for this hexahydrate chromium complex, where the number of waters attached to the chromium is what varies. And we can have coordination isomers, where the ligands to two different metals in our complexes. So in this example of a coordination isomer, we have amine ligands attached to cobalt, and we have cyano-ligands attached to chromium in our two complexes. Or we can have chromium attached to the amine ligands and cobalt attached to the cyano-ligands. So we've switched out either which metal is attached to the ligand, or you can think of it as switching the ligands on the metals. We can also have isomers that are more similar to the organic isomers that you've looked at before. So if we have square planar complexes, we can have cis-trans isomers. If we have 2 A ligands and 2 B ligands, then we can have where the B ligands are next to each other and the A ligands are next to each other. Or we can have the trans form where they're across from each other. If we have 2 of ligand A and then B and some third ligand, then we can still have a cis and trans form, one where the 2 A's are next to each other and the others are on the other side, and one where the A's are across from each other and the others are across from the B and C ligands. If we have 4 different ligands attached to the metal, and we still have a square planar complex, then we have a little bit more complicated situation. We can have A trans to B, A trans to C, and A trans to D, and that pretty much takes care of all the possibilities. You can think about it differently, like think about what's trans to D, for example, but that pretty much sums up the 3 possibilities. If we have ligands that are bidentate, so in this case we have an A and B that are actually the ends of a bidentate ligand, then we can have a form where A is across from B on the other ligand, right? Or where A is across from A on the other ligand. These are still basically cis-trans isomers. All right, if we have tetrahedral complexes, then we can only have optical isomers. And in the case that we have essentially a chiral center here where we have 4 different ligands attached to the metal, then we can have these mirror images occurring. If we have instead bidentate ligands, then we can have mirror images. Since we talked about Berry pseudo-rotations and we talked about how the square pyramid can interchange with the trigonal bipyramidal structures, and because they're so similar in energy, the 5 coordinate complexes are what's said to be not stereochemically rigid. And so unless we have ligands that are bi or polydentate, we really have interchange of all the positions. It is important to note the names of the positions. So down part here where there's a linear portion, these are the axial ligands. And the ones around the middle here, you can think of as being sort of like a circle. Those are the equatorial ligands. In a square planar, in a square pyramidal structure, you still have an axial position, and then these 4 are referred to as the basal positions. In octahedral complexes, we have a possibility where we have all 6 ligands are the same. That doesn't have any isomers. We have a possibility where 5 ligands are the same and 1 other ligand. And while there aren't any isomers, there are different positions. So you can have reactions that might move them around, for example. So if we have a B ligand in what's really sort of an axial position, then that would be distinct from having a B ligand in this more equatorial position. Functionally, they're the same. They're not actually isomers of each other, but there are distinctions to the different locations. If we have 4 of one kind of ligand, some other ligand, so this case here, now we can have cis and trans isomers. So the B ligands can be either across from each other or they can be next to each other. If we have 3 of each type of ligand, we can have what are called facial and meridional isomers. In the facial isomers, the 3 ligands that are the same, so if we look at the A ligands, are all on the same face of the octahedron. If we look at the meridional isomer, which is abbreviated MER, then the 3 lie in the same plane instead of on the same face. And you can look at the A, they're also in the same plane, but it's a little harder to see. We have a little bit more complicated case, and there are a couple of mistakes on these slides, and so I've terrible handwriting. But if we have 2 of ligand A, 2 of ligand B, and 2 of ligand C, then we can have an all trans case where each is across from its own type. We can have 1 ligand that's trans and the other ligands are all cis. So in this first one, the A are across from each other and the B and C are cis. We can have B trans and the others A and C are cis. And we can have C trans and then A and B are cis. And we can have 2 enantiomers where all of the ligands are cis to each other. So if you look at A, B, or C, they're all cis in both of these cases. If we throw in the complexity of bidentate ligand, then we can have some other forms happen. We can have, so in this case, we have 2 of one kind of monodentate ligand, chloride is the case here, and 2 ethylene diamine. So these curves and the nitrogens represent the ethylene diamine. bidentate ligands. And of course, the CLs are the chlorides. So we can have two forms where the chlorides are cis to each other. And then the ethylene diamines are actually cis to each other as well. And we can have one where the chlorides are trans, and then the ethylene diamines are essentially trans from each other. And then there are two enantiomers, which have some really interesting properties, where the ethylene diamines, if we have three ethylene diamines, form these two distinct enantiomers. So let's look at those, that last one. So these two enantiomers, let's look at those a little more closely. So these are optical isomers and give rise to what are known as chiral compounds in this context. So if you imagine that the metal is at the center of these diagrams, okay, so the metal's here in the middle, and the curves are still representing the ethylene diamine ligands. Then we have either clockwise rotation, if you imagine turning this face clockwise, and this nitrogen would replace that nitrogen, then that nitrogen, for example. Then that's called the delta form. And then on the other hand, we can have a form where we have anti-clockwise or counterclockwise rotation, and that's called the lambda form. So these are a little bit like a propeller from a boat in their sort of geometry. All right, so those are all of the isomers and enantiomers that we're going to talk about. That's all the geometry. There it is. And that's the end of the material for this week. Be sure to read the chapter. It's chapter 9. And look at the other information that's posted online. Have a great week.